Okay, gonna share screen. Okay, so we had just talked about this case, right, where these two vectors, which you can see are not, which, you know, I think it was Jackson who told us about the fact that those are not, that, you know, I didn't prove that you get those answers, but you can, right, get two different answers for the C's. So you would get non-unique components for that vector, right? In along along those two vectors, as if you if you thought of them as a basis. That is, of course, they can't be a basis because they're not linearly independent, right? All right. Well, let's think about just starting with a warm-up question here. So we're going to have a question, and the question is, we're going to try to determine coordinate vector of the vector x is equal to 10, 5, 0. I believe it is 0. Did I write that right? 10, 5, 0. With respect to two different bases. Now here I'm not asking you to tell me if these things are bases. I'm saying they are bases. Okay, so I'm already telling you that they're linearly independent and they span R3. Two different bases for R3. And by R3, as you know, we mean the vector space consisting of 115 vectors in 3 dimensions, X, Y, Z. Okay, that's R3 is not the shorthand for that for in every, you know, instance, right? So if you were in a different math class, R3 would just be, you know, all space, right? Here, when I say R3, I mean along with the vector space of 115 vectors, right? Okay. All right. So we're going to try two bases. So we have what's called the standard. Remember, we talked about the standard bases. Standard basis, which was this set E1, E2, E3. Okay, and remember that E1 is 1, 0, 0. E2 is 0, 1, 0, and E3 is 0, 0, 1. And then with respect also to a second basis, which is V1 is equal to 1, negative 1, 1. V2, oh, come on, pen. V2 is equal to, these are vectors, is equal to 0, 1, 2. And V3 is equal to 3, 0, minus 1. Okay, so this is your job. Now you need to figure out, what do I mean by determine the coordinate vector or the component vector, right? The components, right? So it's really saying, what are the components of X with respect to these three, this guy, this basis, and this basis. Okay, so give it a try. If you don't know where to start, I can help, but try the first one.
I'm not entirely certain what the coordinate vector really even is.
Yeah.
It's
So it's the components, right? So it's the components of that of the vector along with respect to this basis, right? So the first one with the standard basis should be trivial. So see what you can do about that. Once you understand how to do that one, you should understand how to do the next one. Number of bases is a set of vectors that you can express any vector as a linear combination of those, right? That's the whole point of a basis.
so would it be just like 10e to the 1 and 5e to the 2?
Um, okay, but the vector itself with respect to that doesn't have the e's in it, right? Like, how would you write the components? What are the
I thought it
components
was a
of
linear
that?
combination of.
Yeah,
I thought it was supposed to be.
yeah.
Then
But remember that it's the c's, right? When you write a linear combination, you're writing, x equals c1 e1 plus c2 e2 plus c3 e3, right? And then you'll be able to write x as, c1, c2, c3, right? Guys, I'm gonna stop the share for a second so I can just share the actual screen thing, not the whole screen. Give me a second. Because my computer's starting to slow. It's annoying, very annoying.
The final solution, do you want something like this?
Oh, it's too blurry for me to read there.
I can't see my own camera.
Shoot.
Something like this for the final solution.
Wow, I really can't see very well. Remember that so do you have the C's, the values for the C's?
Yeah,
The
they're
first one? Yeah, for the first one, right?
yeah, that's it. Yeah, for the first one.
Yeah, good.
So that's okay. So that's all I have to do.
Ben? Push up. guys still working?
I got an answer for B.
Good. Okay, keep it to yourself for a little bit. Okay, let's take like 5 more minutes and then we'll come back. See how far you can get, those of you who are not done.
So
Mhm.
were the values for C1, 2, and 3 supposed to be equal to on both of them? Or what were we supposed to do after we found for each?
What do you mean?
Well, the values I got for C1, C2, and C3 for B are different than the ones I got for A.
They should be.
All right, so is there anything else I should do?
No, just think about the fact that, we're used to thinking of coordinates, right? Like X, Y, Z, with respect to the basis, right? E1, E2, E3. That's the one we're used to. So anytime you see, oh, a vector is 10, 5, 0, usually it's with respect to the basis E1, E2, E3. But it certainly wouldn't be 10, 5, 0 with respect to any other basis, right?
Okay.
Yeah. One more minute. All right, let's come back and talk this over. All right, so when we look at this vector here, this x vector, like I was saying to Jackson, we often just go like, yeah, that's the x component. 10 is the x component, right? 5 is the y component, and 0 is the z component. That's what we assume when we see that, right? If no one says anything else about it. Okay. But really, that assumption is assuming a particular basis, right? And it's this basis, the E1, E2, and E3, I hat, J hat, K hat, right? That's what this is, or X hat, Y hat, Z hat, if you prefer. That's what this basis is, right? So when you write this down, you're like, yeah, that's the X component, that's the Y component, that's the Z component. You're assuming a basis, okay? But remember, a vector is just an object that lives out in space. Well, just think about the 115 vectors anyway, are just these objects that live out in space, right? They point in some direction, they have a length, but like, there's nothing that says they have to be with respect to X hat, Y hat, Z hat, right? You could have them with respect to any bases, as long as that basis, right? To be a basis, remember, it has to be linearly independent and it has to span R3. So as long as those vectors do that, you can have the X vector, that object that lives out in space, have components along any basis, right? So the assumption we make when we see that vector is that it's x hat, y hat, z hat. That's because we're just so used to that, and you never see any other bases pretty much ever until probably this class and maybe linear algebra class. But you don't see it anymore. You don't see a different basis, right? So here in the next, in part B, so so just FYI, according to, with respect to this basis, then x is just 10, sorry, 10, 5, 0, right? According to this, with respect to this basis. Okay, but now when we look at this basis, we want to know how can I write down x with respect to this basis? Okay. All right, so to do that, we need to set up the equations that tell us the c's, right? Because that's what we did here, and you may not have noticed when you did it, hopefully you actually wrote it out, but you really were writing down, okay, 10 is equal to C1 times this, right, component. So C1 times 1 plus C2 times 0 plus C3 times 0, so just C1, right? And 5 is equal to 0 plus 1 times C2 plus 0 times C3, and 0 is, 0 times C1 plus 0 times C2 plus 1 times C3, and that's why you can write this down, right? Okay, so we need the C's for this. So remember those equations, and I'm just being quick with them, right? Really, you're writing x is equal to C1 V1 plus C2 V2 plus C3 V3. And of course, this becomes 3 equations. We write it all out. And those equations are, let's see, 10 is equal to 1 times C1 plus 0 times C2, so no C2, plus 3 times C3. And then 5 is equal to, let's see, minus C1 plus 1 times C2 minus 1 times C3. And 0 is equal to 1 times C1 plus 2 times C2. Did I do something wrong? I think I did something wrong. Yeah, I did something wrong. Let me back up just a tiny bit. Mess something up. Mess
It
something
was
up.
it's 5 equals -1 plus C2, uh, and then the other one is 0 equals C1 plus 2C2 minus C3.
Right. So this is right here, right?
Yeah.
Okay, yeah, and this one is, come on, pen. So this one is 1 times C1 plus 2 times C2 minus C3, right? Yeah? Minus 1 times C3. This is the equation. I think that's what I got. I messed something up somewhere in my notes. Did I just write the vectors down? Sorry, give me a second because I just messed something up. So, okay, I want to triple check this now. C1 is C1. 8 times C minus 1 plus C2. Yes, okay. And then C1, 2, C2 minus, okay, good on these equations, guys? Okay, all right, so obviously you can sit down and solve these, right, for the C's. That's what you want to do, right? Because once you have the C's, you know that X with respect to, you know, V1, V2, V3 is just going to be C1, C2, C3, right? Yeah? Okay, so what did everybody get for this? Let's see if we have some agreement. What'd you get for C1?
-2.
What?
-2.
-2. Okay. C2.
3.
C2? Anybody?
3.
3? You agree, Jackson? C3? What? C3?
4.
4. Jackson? Good. So that means that the X looks like this, right? It's -2, 3, 4. So this guy here is the vector, is the same exact vector. So if you looked at the vector in space, right? Say the pen is the vector, right? It's, think of it, it's easiest to think let's think about it in the standard basis, right? It would have 10 in the X direction and 5 in the Y direction and nothing in the Z. So Z is, let's say, going in and out of towards you or out of you, right? So no, it would be in the XY plane. That vector is not changed, its direction or length. It's just with respect to these 3 vectors now as their basis, it looks like this. Okay, so this is, -2 is not the X component anymore, right? 3 is not the Y component, 4 is not the Z component. -2 is the component along this vector. 3 is the component along this vector, and 4 is the component along this vector, right?
So it's 4 unit. So it's like -2 units along the first vector.
Yep.
So it's like treating each of them as like a yardstick.
Kinda, yeah. Well, think of this vector. So this vector is pointing out in space somewhere, right? And so now think of that vector with respect to x hat, y hat, z hat. It would be 1 in the x direction, -1 in the y direction, and a 1 in the z, right? And now if you take -2 along that, that's going to go this way, right? It's going to go opposite the vector. So let's say here's the head of the vector. So it's going to go opposite the vector, but along the vector itself. Okay? That makes sense? It's a weird concept because you're so used to x hat, y hat, z hat. Okay, first let's as an aside, let's look at solving. Let's look at solving this using like matrix multiplication. So let's see. Let me show you. All right. So right here, remember we have the A matrix that we usually would check. Like say if you wanted to check if these are linearly independent, you would check the determinant, see if it's non-zero, right? Remember how we made that A matrix? So we have A is, you know, we put the things down the column, 1, -1, 1, right? And 0, 1, 2, right? And 3, 0, -1. And the equation this comes from is this, x equals a times the vector c, where c is, you know, c1, c2, c3, right? So if you think about matrix multiplication, what would you get if you did this, right? You would get 1, 0, 3 times the vector c. So that would give you 1 times c1 plus 3 times c3. And then we do the next one, right? You'd get 5 is equal to minus 1 c1 plus c2, right? And 0. See what I'm saying? So this equation is the equation that you get that represents this, right? Same as this. Does everybody understand that part? Okay. All right. Now, if you want to solve this, right, you would like to say, I'm going to apply the matrix inverse to x on this side, and the matrix inverse to this side as well. You have to do the same thing to both sides. And there's C. And on this side, this becomes the identity matrix times C, which I'm just going to write as C. Okay? And so if we can find the inverse and multiply x, you know, multiply by matrix multiplication on x, we'll get C back. Okay, so let's look at our theorem to remember just real quick to remind ourselves about that. I've got to stop the share and do the other kind of share. Just give me a second. All right, just clean. All right, can you see my theorem to remember? Oh, that's the homework. Never mind. Can you give me a second? I got, oh my God. Here we go. All right, let's go up. Let's go back to our, this theorem here. So this theorem is saying, you know, if we want a solution to the system AX equal B, in this case we have AX equal C, right? Then any of these things are, so if this has a solution, then A is invertible, right? So that means we should be able to find an inverse, which makes sense because if we couldn't find an inverse, then how would you have a solution to this, right? You wouldn't be able to. That doesn't make sense, right? And of course, we know also that means that the determinant is non-zero, blah, 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 those other things. Okay, so let's look at how to do this. So I'm going to use MATLAB, but you can use all kinds of different things. Let me close all these windows. They're driving me nuts. Okay, you can use Python or anything else that can do matrix multiplication, Wolfram Alpha, whatever, right? I'm going to move this over a little so I can see. Okay. All right. So I'm going to define the matrix here, right? Oops, let me move the matrix over so you can see a little bit better. No, go away. Sorry. I'm managing all these windows. Give me a second. It's lame. Okay, here we go. Can you see the matrix A on the screen and MATLAB? Okay. So I'm going to define A in MATLAB. So those of you who know MATLAB a little bit, then you'll see how to do this. So we're going to go 1, 0, 3, and then a semicolon. So that's the first row. Minus 1, 1, 0, second row. 1, 2, minus 1 for the third row, and then we're going to close. So let's see, 1, 0, 3, minus 1, 1, 0, 1, 2, minus 1. Yeah, good? And then we're going to use the inverse function. So we're going to, just to show you that it's not going to yell at us and say it doesn't have an inverse. There's the inverse, okay? Now we're not done because as you can see here, we need to apply that to the X vector to get the C vector. I got to move that over again for you because it's not, you can't see it. There we go, right? So I need to apply this to the X vector. So I need to make the X vector. So X equals, that's the original vector, right? 10, 5, 0. And so we're going to say inverse A, sorry, A, capital A. Star means matrix multiply by X, or X. Now it's saying, hey, matrix doesn't agree because if you look here, when you define a vector like this, it's going to be a row vector. It can't do that, right? That would be, that's not matrix multiplication. It has to be a column vector. So all you have to do is put a little tick mark on the X that turns it into a column. Okay. And there we go. There's our answer. There's our C's. Minus 2, 3, 4, right? So I encourage you when you're doing homework or something to use something like this. Wolfram Alpha, I think, can also do, I've never used it, but Mathematica certainly can do matrix multiplication and inverses of matrices for you, right? So it's a quick way of solving these equations is if you can get to, use a computer to do the matrix algebra for it. Does that make sense? Okay. All right, you just need to figure it out. And I don't know if any of you know Python, but it's easy to do in Python as well. Okay. All right, let's continue. I want to, let me pull this out a little bit again. There we go. I'm gonna make a new layer. Okay. And just to give you, we've been talking about, we've just done this for our R3, but we can do it but for a whole different vector space. So let's consider a polynomial vector, which is 4 minus 2x plus 3x squared, okay? And we want to get what are, determine the coordinate vector, which just means the components, right? Okay, so we want to determine the coordinate vector with respect to the following bases. Okay, A is what's called the standard basis for polynomial vector space, which is the set 1x x squared. And B, the set A equals 2 minus 4x and 5x, oh, come on, do it, come on, computer, 5x squared minus 1. Okay, so let's just do the first one, okay, right now. Quick. You only have 3 minutes. I think you can do it pretty quickly. So figure it out. What are the C's for that?
It'd be 4, negative 2x, 3x squared.
Okay, there's no X's in the C's.
Yeah, just 4, negative 2, 3.
Yeah, exactly. It's 4, negative 2, 3, right? These are like the X hat, Y hat, Z hat kind of basis, right? This is the standard basis for polynomials. For, in this case, it's polynomials of degree 2 or less, right? But you can make it for any degree, right? And so, of course, the C vector is going to be, 4 minus 2, 3, right? Prove that to yourself. All right, so we will start next class with this example. And that is not a 13, that's a curly braces, sorry. Okay? And if you want, you should try to solve this using, your favorite matrix multiplication computer program.
Do you know if Randolph offers a free MATLAB thing that you can download on a computer?
No, that you can't download on a computer, but there are, I'm pretty sure that we have a web version that we can use. Let me check real quick since I'm sitting here.
I mean, I can check on it. I was just wondering if you knew off the top of your head.
In coding class, we had a web.
Right, Zoe? Do you
Yeah.
do you remember how to get to it?
I think you literally just type in MATLAB on like the Google search bar or whatever Chrome, whatever you use, and you have to like sign up. But I'm pretty sure that's it.
So if you say this and then what? Online? Here.
MATLAB MathWorks, I'm pretty sure.
What about down here, MATLAB Online?
Yeah, that's probably any of those will eventually get you to
Get you
the,
there, yeah. Yeah, start
Mhm.
using MATLAB Online. Yeah.
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 And I'm pretty sure you just have to create an account or whatever,
Yeah.
but it's free, I'm pretty sure.
Yeah. That's what we used. So try that. Okay.
Cool.
Yeah, cool. All right, guys. We'll see you next time.
See ya.
Bye.